All right, so after spending a bunch of time trying to convince you of regularity theory, now we're going to point out some reasons that it's hard to see how it could actually work or how it actually reflects the way we think about laws of nature. And if you want to go with it, um, it's going to be in many ways be sort of revisionary, right? So it doesn't really capture our concept of laws of nature, and you have to just say, I guess I was wrong about what I thought laws of nature were. Um, and that's sort of what, Schwartz and Hume were saying in the first place. But here we're going to see how extreme it is, the sort of things that you really have to give up for regularity theory. So here's another account of what regularity theory is, right? We could call it, according to regularity theory, we'll call this naive regularity theory, which we're later going to have to sort of revise a bit. But to start, and Schwartz had his own definition, and this is going to be very similar. Um, we can say that P is a statement of a law of nature if and only if, one, P is universally quantified. This is what we saw before, right? It's going to be a universal generalization in Schwartz's terms for all x's, right? If they interact with y's in a certain way, then this certain thing will happen to the x, right? It doesn't pick out particular, right? There's no laws of nature about Nate and his shirt. They're all going to be more general about objects that have mass and things like that. Number two, P has to be true, right? And in it for all time and for everywhere, right? For it to count as a law of nature. Uh, it has to be contingent. Again, this was also an item in Schwartz's account, right? It can't be a law of mathematics or a law of geometry. Those are not contingent. Those are necessary truths. Uh, laws of nature apply to this universe, but not to every possible universe. And then finally, if P is going to be a statement of a law of nature, it has to contain only non-local empirical predicates apart from logical connectives and quantifiers. So that's a little new, right? That wasn't in Schwartz. There's a reason for that. Um, it's related to, right? We don't want laws that just govern my shirt. Also, we don't want laws that sort of like govern a particular area, right? That's the non-local idea, right? And empirical, again, meaning of the observable world, not about like mathematics and things like that. So it sort of captures some similar stuff, but we'll get to sort of these particular formulations and what they're trying to do. Okay, but at any rate, what you get from these four conditions is that any true non-local generalization that's about matters of fact, right, and not matters of, pure mathematics, um, that's going to turn out to be a law on regularity theory. Again, regularity theory was supposed to be a relatively minimal conditions on what counts as a law. Um, and the general theme of this lecture is going to be that it lets in too many things, right? The regularity theory is maybe a little too minimal. And you're going to have to add some conditions, right, to rule out those bad cases. And even then, it's still probably not going to work out. So to begin, right, suppose it's a matter of fact that all swans, right, on this planet and that we've ever observed in the universe happen to be white, right? Well, they would then make it a law of nature that all swans are right. Um, right? It's a universal generalization, right? It's about all swans for all x. If it's a swan, then it's conditional, like Schwartz said. Right? It meets all the and it's not local, right? It's not about any particular swan or swans in Los Angeles or San Diego or something, right? It meets all the conditions, right? But it's a little unsatisfying, right? Because it doesn't tell us anything about the explanation of the regularity. It just sort of describes the regularity, and that's it. It doesn't tell us why swans are white, right? The law just is a regularity. But this is what regularity theorists are trying to say, right? They want to say, yeah, that's all laws of nature are. Um, so why this talk about local and non-local predicates? We don't want it, right, to be the case that it's a law of nature that everyone in this room is shorter than 6'4". That's just accidental, right? That's a true, right, description, a true regularity. Maybe it's the case that anyone who's ever entered that room is less than 6'4". Nonetheless, that's sort of accidental, right? It would easily break. All you need is for someone taller than 6'4" to walk into the room, right? It doesn't seem like the sort of thing that would be a law of nature. It's a little too accidental. So we rule that out by saying, okay, we can't use local predicates. Laws of nature aren't going to feature phrases like in this room, right? They're always going to apply to the whole universe, right? So living in Australia, right? There's no laws of nature about things living in Australia, right? They have to apply to everything everywhere. There's going to be no laws of nature, right, about being 1 light-second distant from proton A, right? Now, the problem with that is that it's picking out a particular proton, right? What would be fine, what's not a local predicate, is being 1 light-second distant from some proton, right? That's fine. That's sort of what we call predicate. Predicates are just sort of properties, descriptions of things. That can feature in a law of nature. That'll be fine. So that's the reason for this local, non-local stuff, right? We don't want it. We don't want these accidental laws of nature that just happen to be true in one little corner of the universe. Okay, but even if you add that stipulation about like, well, look, laws of nature can't feature sort of like stuff that picks out particular people or particular places. You can still generate that same problem using general predicates, right? So, for example, here's Rick Grush, right? He's a faculty member in the philosophy department at UCSD. And here's a law of nature that totally meets the stipulations, doesn't use any local predicates. All faculty members taller than 6'4" of the university philosophy department that offers philosophy of science in the first of 2 summer sessions, but has not offered it in the last 2 years, and so on, right? Maybe you had to add some more, but you can use general terms that don't pick out any particular university, right? Or don't name any particular university or any particular location. You can come up with a description that picks out only Rick Grush, right? Using totally non-local predicates, right? And once you've done that, right, then if you want to say anything else that happens to be true about Rick Grush, let's say that he typically wakes up after 11 a.m., well, then you've got a law of nature that says all of the tallest faculty members of philosophy departments that have offered philosophy of science in the first of 2 summer sessions, but have not offered it in the last 2 years, will typically wake up after 11 a.m. Well, that's not a law of nature, right? There's no real regularity being picked out there. That's just a fact about a guy, right? But you can sort of formulate it in terms that meet the conditions for being a law of nature, right? So this is a problem for the naive regularity theory, right? That can't be enough, right, for something to count as a law of nature, because it ends up that particular facts about one particular person will be laws of nature if you formulate them correctly, right, or cleverly enough. So we need to say more. We need to add more conditions on this naive regularity theory. So the problem wasn't so much local properties, right? Because again, we can pick out a particular location using totally general non-local predicates, right? We just have to pile up enough of them that there's only one place that satisfies them. What we're really trying to get at, right, is that we want our laws of nature only to involve properties that, quote, carve nature at its joints, right? This is a popular phrase. And sort of what it means is like pick out those properties in the world that really matter, that really make a difference in nature, right? Atomic weight is probably one of those natural properties, right? Being a faculty member taller than 6'4", so on, so on, probably isn't, right? There's probably nothing interesting in common among faculty members that are taller than 6'4", right? Apart from their height. So what are these natural properties? Intuitively know what they are, right? Yeah, atomic weight, mass, acceleration, stuff like that seems like the kind of properties we care about for laws. Yeah, being, right, the tallest flower next to a short tree or whatever, like you could jimmy up all kinds of weird properties, and that's not the kind we care about. But how can we make this more rigorous, right, to distinguish the properties that we want to feature in our laws and the ones that we don't, right? Just saying it's an important property is kind of vague, or a property we care about is not really precise enough, right? There is, I didn't assign this paper by David Lewis to you, right? But he does sort of set up a more rigorous account of what he thinks are natural properties, right? So that's a whole sort of rabbit hole direction you could go down, right? So if you want regularity theory to work, you need some account of what natural properties are, or what the properties that we want in our laws are. And people have done work on that. If that's something you want to pursue for a paper, pursue it. I'm going to stop there, right? I can point you in the direction of Lewis if you're interested. Um, and instead, we're going to talk about some other problems with regularity theory, even if you were able to work out that problem and we're able to sort of make a principal distinction between the types of properties that should feature in laws. There's also the problem of unrealized physical possibilities, right? So again, regularities, I mean, part of the virtue of it is regularities are just statements of what is, right? Swartz thought that was a good thing about regularity theory because he thought, well, if there's necessitarian laws, right, those laws will exist and be true even if there were never, right, any bears or any humans. There'll be laws governing bears and humans. That's not the case for regularity theory. Regularity theory just describes what actually exists, right? So if there's no humans, there's no laws about humans. If there are humans, then we do have regularities, right? We can observe. But there's actually a downside to this this thing that Swartz likes about regularity theory, which is it just so happens, right, that there has never existed in the universe, or we can be fairly certain, any gold spheres with a volume greater than 1 cubic mile, right? Let's suppose that's the case. There's never been a gold sphere bigger than a mile, right? Well, then according to regularity theory, that's a law of nature, right? But you want to think, well, no, I mean, if we really wanted to, we could probably make one, right? If we could gather together all the gold, right, we could probably make a sphere, right? A 1 mile, right, volume sphere of gold. So it's weird to see that's a law of nature. It seems like it could be broken, right? Compare that with a law of nature that says there are no spheres of uranium-235 with a volume greater than 1 cubic mile. That seems intuitively like a proper law of nature, right? Yeah, we can't have those because beyond a certain size, you get an explosion, right? They can never get that big, right, without destroying themselves, right? So regularity theory can't distinguish between those two laws. Intuitively, the law about gold is not a very good or useful one, right? It doesn't really tell us much about the nature of the universe, whereas the uranium one does, right? That tells us something about the limitations of what can be done. So the moral of the gold sphere versus uranium sphere example is that there's plenty of things that just haven't happened as a matter of sort of accident or a matter of fact, right? But you don't want to say they're totally ruled out by laws of nature. There's just things that haven't happened yet. There's an infinite number of things that just haven't happened yet, right? Um, so, for example, right, you could have a race of white ravens, right? If a certain population of crows, right, like sort of migrated to the North Pole, lived there for generations, you would have white ravens, right? So, just because that hasn't happened yet, right? You don't want to say that it's a law that there are no white ravens, right? It could easily happen, right? There could easily be population could eventually evolve. Lots of things will happen in the future. Evolution will take, right, biology in many directions that haven't existed yet. You don't want to say it's a law that it can't happen. Now, another problem for regularity theory comes about just because of the rules of logic. So remember, Swartz said uh, that a regularity theory takes the form of a conditional, an if-then statement. So if you've ever taken logic, you know that if the antecedent, the if part, if that's false, then the whole sentence comes out true. And I won't go into detail to explain that to you. If you've never taken logic, just believe that it's true, right? But it turns out that, strictly speaking, logically, a sentence like all unicorns are pink turns out true because there's no unicorns, right? So because regularities take this form, right, just as a matter of logic, it will turn out that lots of universal statements where the antecedent is false, right, or it talks about something that doesn't exist, are all going to be true generalizations that will end up being laws of nature, right? So it'll turn out to be a law of nature that all centaurs are good at philosophy. Why? Because there's no centaurs, right? So because the antecedent is false, right, nothing is a centaur, then the whole thing turns out to be true logically, and now that's a law of nature, right? So that obviously seems wrong. That's not what we want out of laws of nature, right? Is to have regularities about things that don't exist. Um, but it's even worse than that, right? Um, because it'll also end up being a law that all centaurs are terrible at philosophy, right? Because also that statement will be true because there's no centaurs, right? So now you have two laws of nature that are contradictory. So that's just sort of a more abstract, in principle problem with the logic that's laid out by regularity theory, right? That there are these true generalizations. That leaves it open that you can have, right, these true generalizations that take the form of a conditional and if-then statement. That makes it so you can have laws of nature that contradict each other, and that feels wrong. And even worse, we actually do want to be able to make like laws of nature about things that don't exist, but we don't want them to end up sort of like paradoxical, like all centaurs are good at philosophy and all centaurs are not good at philosophy, right? Here's a sort of law that we would like to have that could govern things that don't exist, right? We want to be able to talk about things that haven't happened and use the laws of nature to prevent like things that we don't want to happen from happening, right? So it's true that all brakeless trains would cause accidents, right? Any train without brakes is going to cause an accident, right? We can say that's a true generalization, right? That's why we don't build brakeless trains, right? We don't need to build trains and have the accidents to know that, right? So regularity accounts that really can't distinguish between like the good sorts of generalizations that describe things that haven't happened or don't exist, and the bad type that just end up in contradictions. You can't really make the proper distinctions, right? We want laws about trains that don't have brakes, right? That will be a useful law to have. We don't want laws about centaurs, right? Contradictory laws about centaurs. So again, something about the logical structure of regularity theory is not really capturing what we want out of laws of nature. Because laws of nature are supposed to, in the end, not just be descriptions, but be used in prediction, right? This is kind of something that Hume says, I don't know, right? Who knows what could happen with the billiard balls later? Okay, fine. Maybe strictly logically, I can't prove, right, that the laws of nature will hold in the future, right? But like, this is kind of the basis of science, right? And regularity theories just don't capture it at all, and it runs into problems because we do use science to predict all the time. That's like why we use it, right? So this same problem of non-existent subjects, right, is going to be a case. You're going to run into problems with that for any law that involves a continuous function, right? So a law that talks about mass or acceleration, right, that can take an infinite number of values. There will be some value of that function that has never been instantiated, right? There will be maybe no object has ever had a mass of exactly right 3.4215674432 grams or something like that, right? Maybe no object has ever right had a velocity of 11.127534444111006 meters per second or something like that, right? It's got to be the case because it's a not only infinite values but like uncountably infinite because they're real numbers, right? So you're guaranteed that laws of nature will feature functions for which a certain value has never been instantiated, right? So Newton's laws, for example, force equals mass times acceleration. So the whole point of Newton's laws, the whole point of those types of laws, we can still make predictions about things with that mass, right? Even if that something with that exact mass has never existed, right? They're still going to be governed by the laws of physics, right? So regularity theory, again, by confining laws to descriptions of what is, right, of regularities we've observed, doesn't seem to give us laws that do sort of one of the very important things laws are supposed to do, which is predict things that haven't happened. And again, strictly speaking, right, it's going to, if a certain mass hasn't obtained, then Newton's laws will be true, but also something that a law that contradicts Newton's laws will also be true. That's the problem with these non-existent subjects is logically they all statements about a non-existent thing come out true, right? And that's not very helpful. That's not helpful for prediction. So this is just a beginning, a taste of some of the objections to regularity theory. Next, we're going to talk about Gretzky. He's going to begin his essay by beating up on regularity theory some more, and then giving us reasons to believe back all the way back to necessitarian theory that we sort of began with as the intuitive default. So all of these objections have responses in the literature, right? Regularity theorists still exist, and they will still keep fighting, adding modifications to the list of conditions, right? If you want to do that, right, in a paper, you could do that, right? Take one of these objections and say, look, all we need to do is add this other condition and that's taken care of, right? That could be an interesting paper. So you're welcome to sort of follow each of these, any of these points, like deeper into the weeds, and that's good territory for a paper. But we'll stop with these and we'll pick it up with Dretsky, and that will be the fourth and final lecture in this week. We've got 4 instead of 3, but they're all relatively